So today I am going to discuss an example on field. So before going to discuss the example, once again I am going to remember you the definition of field. So in order to define a field also, first of all it should be a ring itself, and after that it should satisfy three more conditions. One is commutative property with respect to multiplication. Second one is unity element property. So unity element property. And the third one is every non-zero element in capital are having multiplicative inverse property. So the first one is commutative property, second one is unity element property, and the third one is multiplicative inverse property. So in addition to the ring conditions, if we satisfy these three conditions, then we say that that particular ring is a field. So coming to the example, so we have to prove that q root 2 is equal to set of a plus b root 2, where a comma b are rational numbers, is a field. So we have to prove that the set q root 2 is a field, and the elements in q root 2 are of the form a plus b root 2. So if you want to say an element in q root 2, that should be of the form a plus b root 2, where a comma b are rational numbers. So we have to prove that this particular set is a field. So I am writing q root 2 is equal to a plus b root 2, where a comma b belongs to q. And once again I am considering two binary operations, one is plus and the second one is multiplication. So in order to prove q root 2 is a field, first we prove that q root 2 is a ring. And in the ring, first we have to prove that q root 2 comma plus is an abelian group. Okay. So in abelian group, we are having 5 conditions. So the first one is closure property with respect to addition. So for closure property, we have to consider two elements. X comma y belongs to q root 2. So whenever you consider two elements in q root 2, and every element in q root 2 is of the form a plus b root 2, so that I am writing x as a1 plus b1 root 2 and y also as a2 plus b2 root 2. Clearly these two elements are of the form a plus b root 2. Why? Because whenever you consider two elements in q root 2 and the elements in q root 2 are of the form a plus b root 2, so that we have to write x as a plus b root 2 and y also as a plus b root 2, where a1, b1, a2, b2 are rational numbers. So in closure property, we have to prove that x plus y should also belongs to q root 2. So that I considered x plus y. So here x is nothing but a1 plus b1 root 2 and y is nothing but a2 plus b2 root 2. So now I am adding the first term of x with the first term of y. We get a1 plus a2. And the second term of y, x with the second term of y, we get root 2 into b1 plus b2. So if we observe this summation, clearly this is at the form a plus b into root 2. Okay. Here a is nothing but a1 plus a2 and b is nothing but b1 plus b2. So whenever a1 comma a2 are rational number and b1 comma b2 are rational number, we say that a1 plus a2 and b1 plus b2 is also a rational number. It means a1 plus a2 clearly belongs to q and b1 plus b2 also belongs to q. And this is of the form a plus b root 2. So this clearly belongs to q root 2. It means x plus y belongs to q root 2 for all x comma y belongs to q root 2. So this is closure property. Okay. I consider two elements in q root 2 and I have proved that the sum of those two elements should also belongs to q root 2. So that is closure property. Coming to the second property, that is associative property. So for this property, I have to consider three elements, x comma y comma z in q root 2. So I am writing x as a1 plus b1 root 2, y as a2 plus b2 root 2, and z as a3 plus b3 root 2. Yes, because every element in q root 2 is of the form a plus b root 2, so that I have to write x, y, and z in those forms. So clearly a1, a2, a3 and b1, b2, b3 are rational numbers. So here I considered x plus of y plus z, and I have to prove that x plus y plus z. Okay, so I'm writing the values of x, y and z. So I am writing x as usually and I am adding both y and z. So the first term of y and the first term of z gives a2 plus a3, and the second term of y and the second term of z gives root 2 into b2 plus b3. Now the first term of x with the first term of y plus z gives a1 plus of a2 plus a3, and the second term of x with the second term of y plus z gives root 2 into b1 plus of b2 plus b3. So clearly a1, a2, a3 are rational numbers. And in the set of all rational numbers, clearly the associative property holds with respect to addition. So that I can write a1 plus of a2 plus a3 as a1 plus a2 plus a3. So this is because of associative property in rational numbers. Okay. And in the same way, b1 plus of b2 plus b3 can be written as b1 plus b2 plus b3. Okay. Once again, this is by associative property in Q. Okay, but we have to prove that the associative property in Q root 2. Okay, right. So once again, I am separating the terms as the first term in this bracket a1 plus a2 with root 2 into b1 plus b2, and after that I am writing a3 plus root 2 into b3. So if you split these two terms, we get a1 plus b1 root 2 plus a2 plus b2 root 2, and finally a3 plus root 2 b3. So this is x and this is y, so that we get x plus y plus z. So I consider x plus of y plus z, and I have proved x plus y plus z. So therefore associative property holds with respect to addition. Coming to the next condition, that is identity property. So I consider an element in Q root 2. So clearly x is of the form a plus b root 2. And I am writing 0 as 0 plus 0 into root 2. Why? Because I am writing 0 as 0 plus 0 into root 2 is. So if you want to say 0 belongs to Q root 2, that 0 should also of the form a plus b root 2. So that I am writing 0 as 0 plus 0 root 2. Clearly 0 is a rational number, so that clearly this particular element belongs to Q root 2. And if we add 0 to x, so we get a plus b root 2 plus 0 plus 0 root 2. And finally we get a plus b root 2, which is x. It means if we add any element with 0, we get the number itself. So similarly, if we add 0 plus x also, we get x itself. So that we conclude that 0 is the identity element in Q root 2 with respect to addition. Okay. So after that, we have to prove the inverse property. So in inverse property, we have to consider an element in Q root 2. So once again, x is of the form a plus b root 2, where a comma b are rationals. So whenever a comma b are rationals, we can write minus a comma minus b also belongs to Q. It means they are also rationals. Yes, clearly, whenever 1 comma 2 belongs to Q, we can write minus 1 comma minus 2 belongs to Q. So whenever minus a comma minus b belongs to Q, I am writing minus a plus of minus b into root 2 belongs to Q root 2. Yes, in order to say an element belongs to Q root 2, that should be of the form a plus b root 2. Yes, this is of the form a plus b root 2, where the element a, here a is nothing but minus a, and b is nothing but minus b, clearly rational numbers. So that clearly this element belongs to Q root 2. So and I am naming this element as y. Okay, let y is equal to minus a plus of minus b into root 2. So now I am considering x plus y. So x is nothing but a plus b root 2, and y is equal to minus a plus of minus b into root 2. So if we add these two elements, we get the first element of x with first element of y, we get a minus a, and the second element of x with second element of y, we get root 2 into b minus b, which is equal to 0 plus root 2 into 0, which is 0. It means the sum of x plus y is 0. Similarly, if we consider y plus x also, we get 0. So whenever the sum of two elements is equal to 0, 0 is nothing but the additive identity element, we say that x and y are inverse to each other. Therefore, the inverse of x is y, and hence the inverse property holds. So coming to the next condition, that is commutative property. So for commutative property also, we have to consider two elements. I have considered x comma y. Once again, I am writing x is equal to a1 plus b1 root 2 and y is equal to a2 plus b2 root 2. So you don't forget to remember that every element in our set is of the form a plus b root 2. Okay. So where a1, a2, b1, b2 are rational numbers. So in commutative property, we have to consider x plus y. So I'm writing the values of x and y. Okay. And I am now adding the first term of x with first term of y, which gives a1 plus a2. And the second term of x with second term of y gives root 2 into b1 plus b2. Since a1, a2 and b1, b2 are rationals, and in the set Q, clearly the commutative property holds so that a1 plus a2 can be written as a2 plus a1. So this is by commutative property in rationals. Okay. Similarly, b1 plus b2 can be written as b2 plus b1. And if you separate these two terms, we get a2 plus b2 root 2 and a1 plus b1 root 2. So therefore, this is y and this is x. Therefore, we get y plus x. So I consider x plus y and I have proved y plus x. This is commutative property with respect to addition. Therefore, I have proved all the conditions of abelian group. Therefore, we can say that q root 2 comma plus is an abelian group. So in the ring definition, next we have to prove that q root 2 comma dot is semigroup. Okay. And in semigroup, we are having two conditions. One is closure property and the second one is associative property. So coming to the closure property, we have to consider two elements in q root 2. I am considering x comma y. Okay, x is nothing but a1 plus b1 root 2 and y is nothing but a2 plus b2 root 2. Yes, this is by definition. And a1, a2, b1, b2 belongs to q. And in associative and in closure property, we have to prove that the product of those two elements should also belongs to q root 2. So that I consider xy. So x is nothing but a1 plus b1 root 2 and y is nothing but a2 plus b2 root 2. So and if you multiply these two terms, so the first term of x with the first term of y, we get a1, a2. First term of x with second term of y gives a1, b2 root 2. Second term of x with first term of y gives a2, b1 root 2. And second term of x with second term of y gives 2, b1, b2. And if you write these terms as a1, a2 plus 2, b1, b2, and if you take root 2 common in these two terms, we get root 2 into a1, b2 plus a2, b1. So whenever you have written the summation as in this form, clearly this is of the form a plus b root 2. Okay. So where a1, a2 plus 2, b1, b2, we have to treat this as a, and a1, b2 plus a2, b1, we have to treat this as b. So clearly this is of the form a plus b root 2. So clearly the element in the place of a is a rational number. So whenever a1, a2, b1, b2 are rational numbers, so that the product of two rational numbers is also a rational number, and the sum of two rational numbers is also a rational number. So that this element is a rational number, and this is also a rational number. So, and this is of the form a plus b root 2. We have to treat this as a and this as b. So clearly this is of the form a plus b root 2, and every element is of the every element in the form a plus b root 2 clearly belongs to q whenever a comma b are rationals. Yes, you are saying that clearly a is a rational number and b is a rational number. Therefore, this particular element belongs to q root 2. Therefore, I consider x comma y in q root 2, and I have proved xy belongs to q root 2. This shows that the closure property holds with respect to multiplication. So coming to the next property, that is associative property. For associative property, I have to consider three elements: x comma y comma z. So once again, x is nothing but a1 plus b1 root 2, y is equal to a2 plus b2 root 2, and z is equal to a3 plus b3 root 2. So where a1, a2, a3, b1, b2, b3 are rational numbers. So in associative property, we have to consider x into yz. So I am writing the values of x, y, and z. And I am writing the value of x as usually. Now I am multiplying yz. So the first term of y with the first term of z, we get a2, a3. And the first term of y with the second term of z, we gives a2, b3 root 2. Similarly, the second term of y with first term of z gives a3, b2 root 2. And the second term of y with second term of z gives 2, b2, b3. Okay. And after that, once again, I am writing the value of x as usually. And in the product yz, I am writing the terms as a2, a3 plus 2, b2, b3 in one bracket. So I am writing those two terms in one bracket. And in the remaining two terms, I am taking root 2 common so that we get root 2 into a2, b3 plus a3, b2. Okay. So in this in this summation, I am writing other than root 2 terms in one bracket and root 2 terms in one bracket. Okay. So now we have to multiply the product yz into x. Product yz with x. So the first term of x is a1 and the first term of yz is a2 a3 plus 2b2 b3. So that I have written a1 into a2 a3 plus 2b2 b3. Once again the first term of x with the second term of yz. So we get a1 into root 2 of a2 b3 plus b2 a3. And the second term of x with the first term of yz we get b1 root 2 into a2 a3 plus 2b2 b3. And finally second term of x with second term of yz we get 2b1 into a2 b3 plus b2 a3. So if we write neatly by multiplication, by multiplicating we get a1 a2 a3 plus 2 a1 b2 b3. And also I am writing the other than root 2 terms here itself, so that we get 2 a2 b1 b3 plus 2 a3 b1 b2. And in the remaining terms I am taking root 2 common, so that we get a1 a2 b3 plus a1 a3 b2 plus a2 a3 b1 plus 2 b1 b2 b3. Okay, so I am writing all these terms as a plus b root 2 form. I am writing all these terms in the form a plus b root 2, other than root 2 terms as one term and root 2 terms as another term. Okay, this is the value of x into yz. So now if we consider xy into z, xy into z. So similarly in the same way we can also get the value of xy into z as above. So that I am writing directly that the value of xy into z as x into yz. So therefore we say that x into yz is equal to xy into z. So we need not to prove, because I have already done that x into yz. In the same way, if we calculate first xy and if we multiply the value of xy with z also, then also we get the same value as x into yz. So therefore x into yz is equal to xy into z. Therefore associative property holds. Therefore we say that q root 2 comma dot is semi-true. Okay. So after that we have to prove distributive properties in ring definition. For distributive properties also we have to consider three elements. So I consider x comma y comma z, and I am writing x as a1 plus b1 root 2, y and z, where a1 a2 a3 and b1 b2 b3 are rational numbers, right? So in the distributive property we have to consider x dot of y plus z. This is left distributive property. So we have to write the values of x, y plus z. Okay, so first we have to add the y plus z, so that we get a2 plus a3 plus root 2 into b2 plus b3. And after that we have to multiply x with y plus z, so that we get the first term of x with the first term of y plus z gives a1 of a2 plus a3. The first term of x with the second term of y plus z gives a1 root 2 into b2 plus b3. And the second term of x with the first term of y plus z gives b1 root 2 into a2 plus a3. And the second term of x with the second term of y plus z gives 2b1 into b2 plus b3. So once again, if you multiply this with a1, we get a1 a2 plus a1 a3. And if you multiply with a1, gives a1 b2 plus a1 b3 into root 2. And if you multiply with this with b1, we gives root 2 into b1 a2 plus b1 a3. And finally here we get 2b1 b2 plus 2b1 b3. So once again, if you write other than root 2 terms as one term, and if you take root 2 common, we get another term. Okay, this is at the form a plus b root 2. And this is the value of x into y plus z. Similarly, if you calculate xy plus xz also, we get the same value as x into y plus z. Okay, so I am writing that xy plus xz is also equal to x into y plus z. So this is left distributive property with respect to this is left distributive property. Similarly, in the same way, we can also prove right distributive property. So that is y plus z into x is equal to yx plus zx. So we need not to prove. So clearly, right distributive property also holds. So for distributive properties also holds. Therefore, we say that q root 2 comma plus comma dot is a commutative ring. Sorry, is a ring itself. So whenever it satisfies commutative property, then we can say that that is a commutative ring. Okay, so for that I am after ring conditions, we have to prove three more conditions. That is, one is commutative property. So here I consider commutative property. For commutative property, we have to consider two elements, x comma y. X is equal to a1 plus b1 root 2, y is equal to a2 plus b2 root 2. So I consider xy. So we have to multiply x and y. So after multiplying these two terms, we have to write those two terms in the form a plus b root 2. Okay. So every time I'm writing that, so that you have to write after multiplying x and y, we have to write the terms as a plus b root 2. Similarly, if you multiply yx also, we get the same value as xy. So that I am writing directly the value of yx as xy. Therefore, xy is equal to yx. This is commutative property with respect to multiplication, and it clearly holds with respect to multiplication. Right. Coming to the next property, that is unity element property. So unity element property, if you want to say that ring is having unity element property, we have to prove that 1 belongs to capital R. So I am writing an element of the form 1 plus 0 into root 2. So the value of 1 plus 0 into root 2 is nothing but 1. It means I am writing 1 as 1 plus 0 into root 2. Clearly this is of the form a plus b root 2, where a is nothing but a is nothing but 1, and b is nothing but 0. Clearly these two are rational numbers. So that I am writing 1 as 1 plus 0 into root 2. Clearly this belongs to q root 2, because this is of the form a plus b root 2. Okay. And if you multiply any element with 1, we get the number itself. Here I am multiplying x with 1. So when we multiply x with 1 or 1 with x, we also get x itself. So therefore 1 belongs to q root 2. So whenever 1 belongs to q root 2, we say that unity element property also holds in capital R. Sorry, in q root 2, in our set q root 2. Okay. And finally, we have to prove multiplicate inverse property. So for multiplicate inverse property, we have to consider a non-zero element in our set. So that I am writing 0 not equal to a plus b root 2 in q root 2. So the multiplicate inverse of a plus b root 2 is 1 by a plus b root 2. Yes, if you want to write multiplicate inverse for 2, we have to write 1 by 2. Similarly for 3 is 1 by 3. Okay. In the same way, I am writing the multiplicate inverse for a plus b root 2 is 1 by a plus b root 2. And whenever we are having root terms in the denominator, we have to rationalize. Okay. So the multiplicate inverse is a plus b root 2, what we have to set, and we have to rationalize this multiplicate inverse. So that I am rationalizing that the multiplicate inverse. Here in denominator, we are having a plus b root 2. And the rationalizing factor for the denominator is a minus b root 2. So we have to multiply both numerator and denominator with a minus b root 2. So that we get in the numerator a minus b root 2 itself, and in the denominator we are having a plus b into a minus b form, so that we get a square minus 2b square. And if we separate this term as a by a square minus 2b square minus b by a square minus 2b square into root 2. So if this is of the form a plus b root 2, once again this is of the form a plus b root 2. Whenever an element is of the form a plus b root 2, clearly that belongs to q root 2. It means every non-zero element having multiplicate inverse in q root 2. Therefore multiplicate inverse property also holds. So in addition to the ring conditions, if you satisfy commutative property, unity element property, and multiplicate inverse property, we say that q root 2 comma plus comma dot is a field. Thank you.